How do we tailor the properties of steel for a desired application? How can we make a metal strong or tough? How can we optimize properties, and what information can help in defining how we heat treat metals? In this video, we will try to answer these questions by looking at how heat treatment is critical in achieving the optimum properties and how we can either soften or harden a metal through producing different microstructures. We will review the different heat treatments, the microstructures formed, and how we predict what these might be. Along with the addition of chemical elements, heat treatment is probably the most important process in controlling the properties of metal. It involves heating solid metal to a defined temperature, followed by a suitable cooling rate in order to achieve the desired material properties. Heat treatments are primarily conducted to either soften or harden the steel, depending on its final application and manufacturing process. This softening treatment is often referred to as a conditioning process and will lower strength and hardness while increasing toughness and ductility. Conditioning includes two heat treatments called annealing and normalizing. The hardening process does the opposite. It increases strength and hardness while lowering toughness and ductility. This includes two processes called quenching and tempering and age hardening. The specific heat treatment used in manufacturing will depend on the metal chemistry, the size of the part, and the required properties. The three main structures that are achievable through heat treatment are perlite, bainite, and martensite. For the majority of heat treatments, we cool from the austenitic temperature region. The austenitic region is where most of the alloying additions go back into solution, and this is shown here in the iron-carbon equilibrium diagram. This diagram shows the structures formed under slow cooling in iron as a function of temperature and carbon content. As we cool through the transformation region, we can create different structures by altering the cooling rate. If we want to achieve perlite, the softest structure, we need to cool slowly enough so that this is formed. To achieve martensite, the hardest structure, we need to cool quickly enough to ensure that perlite or bainite is not formed. The speed of these cooling rates depends on a given steel composition, and there are various diagrams that help to predict the different structures formed. These will be discussed later in this module. Quench and tempering is probably the widest used of the heat treatments to harden steel and consists of heating the material to approximately 15 degrees Celsius or 60 degrees Fahrenheit to the austenitic range. For steels, this is usually somewhere between 700 degrees to 1000 degrees Celsius or 1290 degrees to 1830 degrees Fahrenheit. It is then held at this temperature until the material is fully transformed to austenite. This whole time takes into account the dimensions of the component. The material is then removed from the furnace and submerged, usually in an agitated liquid, in a process called quenching. This causes changes in the microstructure as the component cools rapidly down to around 200 degrees Celsius or 390 degrees Fahrenheit. This quenching causes none or very little carbon to precipitate as iron carbide. It produces a feather-like structure called martensite, which distorts the internal structure. This additional stress makes it difficult for defects on the atomic scale, called dislocations, to move around in response to the applied load, causing the material to become stronger. The formation of martensite is only achieved if the material exceeds a critical cooling rate. If not, the microstructure formed will be either bainite, perlite or ferrite, or a combination of these. This is the reason why components of different sizes processed the same way may have vastly different properties, and also why the surface properties may differ from the center, which would cool slower than the surface. The quenching operation will increase the hardness and strength of the steel, but will drastically decrease the ductility and toughness. The aim of tempering is to soften the steel back, achieving the desired combination of properties. Tempering will considerably improve toughness and ductility while still maintaining a high strength level. Tempering consists of heating the steel to a temperature below the austenitic range, usually somewhere between 500 degrees to 650 degrees Celsius or 900 degrees to 1200 degrees Fahrenheit, and holding at this temperature for a specific time period. During this process, the hard brittle martensite dissociate into ferrite and iron carbide, producing a structure called tempered martensite, which has lots of fine particles dispersed through the ferrite. This will give the optimum combination of strength, hardness, toughness, and ductility. The ratios of these properties can be refined through the time and temperature of the tempering. Age hardening, sometimes called precipitation hardening, is used to increase the strength and hardness of some stainless steels and nickel-based alloys. It follows similar steps to quench and tempering, in such that the material is heated to a temperature to dissolve all the atoms into solution. It is then quenched at a cooling rate fast enough for the atoms to remain frozen in solution. The final step differs from tempering, as it is designed to harden the steel as opposed to soften it back. It is called aging and involves the controlled reheating to around 450 degrees to 650 degrees Celsius or 840 degrees to 1200 degrees Fahrenheit to cause some atoms to precipitate. These create strain in the structure, and again this makes it difficult for the dislocation effect to move in response to the applied load, making the material stronger. Conditioning treatments can be used to obtain the final properties of a steel, or it can be used as an intermediate step in order to ensure that the material will not crack following rolling, casting, forming or forging. It can also be used to get the material into a state to aid in machining. In both normalizing and annealing, the material is heated to the austenite range and then slow cooled. This is done in still air for normalizing and in a furnace for annealing. A normalized structure can also be tempered to alter the properties slightly. Any gases that need removing, for example hydrogen, will be done as part of this process. Both treatments leave the material homogeneous, soft and ductile, but because normalizing is cooled in air, the strength and hardness of this structure will be greater than the annealed one. Some nickel alloys and stainless steels are used in the annealed condition to aid in corrosion resistance. Due to the slow cooling rates present in normalizing and annealing, a perlite structure is likely to form. Perlite consists of alternate layers of iron carbide, also known as cementite, and a pure iron structure called ferrite. During cooling, the austenite, which has higher solubility for carbon, starts to turn to ferrite. But because this ferrite cannot accommodate the higher concentration of carbon, the structure develops in alternate layers of cementite and ferrite. This perlite is often present with ferrite, and depending on the carbon content, the perlite and ferrite will be present in differing ratios. If the cooling rate is too fast for perlite, but not quick enough to produce martensite, a structure called bainite will form. Bainite is of medium hardness and lays at a medium cooling rate in between perlite and martensite. Initially, ferrite is produced, but because the cooling rate is quicker than perlite, the structure does not form in layers of ferrite and iron carbide, but instead the iron carbide starts to precipitate from the remaining carbon-rich austenite, forming a structure that consists of ferrite and particles of iron carbide. Depending on the cooling rate, these iron carbide particles can be more elongated. This is called upper bainite and is the slower cooled of the two structures. The other, lower bainite, forms at faster cooling rates and contains ferrite with finer disc-like particles of iron carbide. An annealing process used in cold rolling or forming is a subcritical or process annealing. This is used to reduce internal stresses after manufacture or to enable further processing. In this process, the steel is not heated all the way up to the austenitic range, but is heated just below the ferrite to the austenite transformation temperature, usually around 500 degrees to 650 degrees Celsius or 930 degrees to 1200 degrees Fahrenheit. The material is then held for the desired amount of time to cause softening through structural changes, primarily grain recrystallization and grain growth. Generally, the higher the alloy content, the easier it is to form martensite, and this ability to form martensite is known as hardenability, meaning a steel with low hardenability requires a faster cooling rate to attain the same hardness at a given location than a steel with high hardenability. Knowing what structures will form in a steel can be aided by two diagrams called the continuous cooling transformation and time temperature transformation diagrams. Both these diagrams show what structures will be achieved under different heat treatment conditions. They will also show the effect that chemical elements will have on the structures formed. For example, elements like carbon, manganese, nickel, molybdenum, chromium and vanadium make the steel more hardenable, making it easier to form martensite at slower cooling rates. Time temperature transformation diagrams are used to understand what microstructures will form as a function of temperature and hold time. This means that heat treaters can use this diagram to understand what structures might be formed if a component is cooled from austenite and held at a given temperature for a given time. This is possible because if we hold austenite at a temperature where it is unstable, eventually austenite will form into a different microstructure in a process called isothermal transformation. The diagrams assist in conducting two treatments that help to minimize distortion, residual stresses, and risk of cracking. These are called mertempering and austempering, and they are essentially the same process. They involve cooling at a sufficiently quick rate to an intermediate temperature to form the desired structure, holding to enable the temperature at the center to equalize with the surface to reduce internal stresses, and then cooling the material to room temperature. For mertempering, the material is held in the martensite region, and in austempering, the component is held in the bainite region. A salt or oil bath is often used to hold a sufficiently high intermediate temperature. Time temperature transformation diagrams provide a good starting point to aid in heat treatment, but because they are interested in the isothermal transformation of austenite, they are only of limited use. To accurately predict the heat treatment response and thus microstructure of different steels of different sizes quenched in different liquids, we need to use a different chart called a continuous cooling transformation diagram. This has greater practical use for heat treaters. Continuous cooling transformation diagrams present data in two ways. The first is to plot microstructures as a function of temperature and cooling rate. From this, we can superimpose the cooling rate of our component either at the surface, center, or any distance in between, and we can predict which microstructure will be formed. The second is to represent the cooling rate at the center of different diameter bars for cooling in air, oil, and water. This type of CCT diagram is a convenient way to look up the bar diameter we are quenching and the cooling medium used, and again predict the structure at the center of the bar. Both of these ways are often presented on the same diagram, along with the hardness, and this will enable the heat treater to start to predict the properties of the steel. There are more specialized heat treatments that we have not covered here that use special processes and environments to control specific material properties. These processes include quenching with polymers and brines using surface hardening by just heating and quenching the outer few millimeters. Continuous furnaces can be used to automate the process, and special environments like in nitriding can also be used. So to summarize, heat treatment is critical in achieving the optimum properties and is used for either softening or conditioning a metal, like in normalizing and annealing treatments, or it can be used to harden a metal, like in quench and tempering, or age hardening. These treatments will produce three main microstructures, either perlite, bainite, or martensite. The specific heat treatment used in manufacturing will depend on the metal chemistry, the size of the part, and the required properties. Two diagrams can aid heat treaters in predicting the structure and properties in metals. These are called the continuous cooling transformation and time temperature transformation diagrams.